This is part B of chapter 11, Simplify Radical Expressions, and these rules apply to simplest form. It's not that these things are illegal in mathematics, it just means if you see any of these things, it's not in simplest form. So the first thing is we're not allowed to leave fractions under the radicand, and remember that means we can't have a fraction under the square root symbol if it's a square root, or the cube root if it's a cube root. We're also not allowed to leave radicals in the denominator. And the next one's a little bit tricky to understand until we've done it. No perfect square factors other than 1 in the radicand. So we need to break up square roots using perfect squares whenever we can. The other than 1 is kind of like the idea of saying when simplifying a fraction, make sure no number goes into both the numerator and the denominator, and we really mean no number other than 1. Rationalizing a denominator is the process for how we take care of a situation like this. If there is a radical in the denominator, there's a mathematical way to take care of that, and that's called rationalizing. Now, a couple properties of radicals. First of all, the square root of a product is the product of the square roots. So the square root of a times b is the square root of a times the square root of b. Now the way we use that, something like the square root of 9x, we can break that up into the square root of 9 times the square root of x, and the square root of 9 is 3. Quotient properties. First of all, if you have a fraction under a radical, you can break that up into the square root of the numerator and the square root of the denominator. So the square root of 4/9, instead of punching that up on a calculator, what we would do is break it up into the square root of 4 of the square root of 9, because the square root of 4 is 2, and the square root of 9 is 3. Now, I didn't get the chart copied into your packet, sorry about that, and you don't have to get to the point where you do all of the lines here, but I would like you to make a table where you at least have the square root of n and n, and I'm doing this in a certain way. It might seem a little backwards, you might have organized it a different way, but n will be the perfect squares, and the square root of n, so the square root of 1 is 1, the square root of 4 is 2. If n is 9, the square root of 9 is 3. If n is 16, the square root of 16 is 4, and so on. And remember, we need to be able to recognize these perfect squares because we'll be using them in simplification. And again, they go on forever. Where we're going to stop here, looks like we'll stop at 10. But these are numbers you'll need to recognize so that you can use them to simplify. Now you'll also have to be real careful, and this is where you'll need to check your notes and check your work with the back of the book. I'm not asking you to change this to a decimal. I'm asking you to simplify it. So we'll use that product property. The square root of 75 can be broken up into a radical times a radical, and we don't always put the multiplication sign in. So now I look back at my list and I find the biggest perfect square other than 1 that goes into 75. Well, I'm actually going to start down here. 75 is right here, and when I say goes into, I mean evenly. So I know 64 goes into 75 but not evenly. So 64 is not a factor of 75, neither is 49, neither is 36. 25 is. Okay, so that's the number I want, and this square root will be whatever it takes to get me back to 75. 25 times 3, so the square root of 25 times the square root of 3 is the square root of 75. The square root of 25 is 5. Now, those two numbers are equivalent. Just like if you simplify a fraction, you get a value that's equivalent, but it's in simpler numbers. And this is considered to be simpler than the square root of 75. Now for part B, the square root of 12x squared. Well, the perfect square that goes into 12, and now if you're thinking about something like 6 times 2, remember, we need a perfect square. So 4 is the perfect square factor we need. Now what I'm going to do is not that. Well, okay, I guess I did that, but I didn't want to do that. That's what I want. And the reason I want that is the square root of 4 is 2. The square root of x squared is x. And the square root of 3 is left over for the square root of 3. Now, we can also multiply square roots by other square roots. The square root of 8 times the square root of 2 is the square root of 16, which is 4. Part D, we'll put it all together and then see if there's a way that we can take it apart differently. Now, there's a big difference between under the radical and outside the radical. If you want to think of a positive 1 there, you certainly could. We'll start with the outsides. 1 times 2 is 2. A square root times a square root. Well, I have 5 times 1 for 5. X to the third y times x is x to the fourth y. Now, there's no way to simplify this 5 using square roots. However, x to the fourth is a perfect square. So I'm going to list that first, and then the leftovers, 5y. The square root of x to the fourth is x squared. And that is simplified. We have a fraction we can break up into the square root of a numerator, the numerator over the square root of the denominator. Square root of 11 cannot be broken up. There's no perfect square factor other than one that goes into 11 evenly. The square root of 49 is 7. That's done. Some of you will have the answer to part F written down before I even, okay, it's t over 6. You could do an in-between step where you break it up like we did here. Or you could just think t over 6 times t over 6 is t squared over 36. Square root of 16z to the fourth. This might be another one where maybe you can just think through it. Big difference between inside and outside. 4 times 1 is 4. Square root of 5m squared n. Perfect square factor is the m squared. 5n will be left over still into the square root. Square root of m squared is m. Now there are a couple ways that we could approach part I. We could simplify 15/25. However, I really like the fact that I have a square root of 25, so I'm not going to simplify it. In fact, that would be more work. I'd still have to do some other things that I haven't even learned yet. So, since I have that perfect square in the denominator, now before we circle that, is there a perfect square factor of 15 other than 1? Well, 4, 9, 16, that's done. Now, this is a situation where we need to rationalize the denominator. We have a denominator with a radical, and it's not a perfect square. And that's on the list of things we're not allowed to have. So we're going to do something pretty tricky here. We're going to multiply this by something and not change its value. Well, there's only one thing we can multiply by and not change its value. The only thing we can do is multiply that by 1. Well, but that doesn't seem to do anything. But that's the only thing I can do. So let's see, I have to multiply it by 1. Well, it's a fraction. Maybe I'll multiply it by a fraction. Same thing. Well, There are lots of fractions in the world that equal 1. How about this one? Square root of 5 over the square root of 5. Yeah, that's going to be it. Multiply by the square root of 5 over the square root of 5. I know that equals 1 because it's a fraction that has the numerator and the denominator the same. I get the square root of 10 over the square root of 25, which is the square root of 10 over 5. I'm going to have you try part K on your own, and we will do part L in class. In fact, we'll do part L a couple different ways. We'll move ahead to this, add or subtract the radical expressions. We'll bring back the idea of like terms. We can only add terms that have the same radical parts, just like we can only add terms that have the same variable parts. So these two terms will go together. Now, eighths plus eighths are still eighths. X's plus x's are still x's. 7 times the square root of 5 plus 4 times the square root of 5 is 11 times the square root of 5 minus the square root of 11. That's as far as we can go. That is done. Now you look at part B and you might say, well, we can't even do anything. This is done. This is why we still go through the process of breaking up radicals. The square root of 18 is the square root of 9 times the square root of 2. And the square root of 9 is 3. And 2 times the square root of 2 minus 3 times the square root of 2 is negative 1 times the square root of 2. Go ahead and put the 1 in if you like, but you don't need to write it in. Now we'll distribute 1 root 7 times 2 root 7. And now be careful, we're multiplying here. Like fractions, we can multiply anything we want. Is 2 root 49. The square root of 7 plus the square root of 3 is the square root of 21. Now the square root of 49 is 7. And 2 times 7 is 14. Now, before I circle that, is there anything perfect square that goes into 21 other than 1? Nope, that's done. 2 binomials. You could use the box method. I will FOIL. I'll need to do 4 times 3. I'll need to do 4 times negative 2 root 3. I'll need to do 3 times the square root of 3, and I'll need to do the square root of 3 times negative 2 times the square root of 3. I'll get a 12, a negative 8 times the square root of 3, a positive 3 times the square root of 3, and a negative 2 times the square root of 9, which is negative 2 times 3, which is negative 6. So when I put together what goes together, a positive 12 and a negative 6 makes a positive 6 minus 5 times the square root of 3. There are a couple more for you to try. I'd like you to try part C and part D. Number 4 we will look at in class.